start today's lecture. So just as a review, a chiral center. So a chiral center, our shorthand for a chiral center, is a point in a molecule where 4 different groups or atoms are attached to a carbon. So for example, 5-bromodecane is chiral because we have a hydrogen, a bromine, a butyl group, and a pentyl group. Perfect. Now, if 2 substituents on a carbon are the same, there is an axis of symmetry and the carbon is achiral. Okay, so let's take a look at this carbon right here. So let's take a look at this carbon right here. Does this carbon that I've boxed, and don't be shy to type in the chat, does this carbon that I've boxed have 2 identical substituents? Does it have 2 of the same groups attached to it? Or does it have 4 different groups? Yep, I see a lot of people typing yes, right? We have 2 methyl groups. So this center is not a chiral center. Is there a chiral center in our molecule? So if I number my carbons 1, 2, 3, 4, is there a carbon that is a chiral center? What carbon is a chiral center? What carbon has 4 different groups on it? What carbon has 4 different groups? 2, exactly right, exactly right. So we have this isopropyl chain. We have a chlorine, we have a hydrogen, and we have an ethyl group. Yep. So the way that we denote chiral carbons is often with a star. That star is indicating this is a chiral center. It's a nice shorthand to keep in mind. Does that make sense so far? Let's try another example. Let's try and let's number all of our sites. So 1, 2, 3, 4, 5, 6. I'd like you to take a moment and I'd like you to state in chat which of these 6 carbons are chiral centers. Which of these 6 carbons have 4 different substituents? And to help everyone with that, let's draw out our hydrogens. Don't forget to draw your hydrogens. Otherwise, you're going to be having a lot of trouble with this next chapter. So what carbons in this layout are chiral? What carbons are chiral centers? Take a moment to type in chat. And there are at least 2 answers to this, if not more. Yep. Can I get some more responses in the chat? There are plenty of correct answers for this. Don't be shy to type. So I see a lot of people typing 3 and 5. That is correct. So for carbon 3, we have an ethyl group, a methyl group, a hydrogen, and an oxygen. Let's take a look at carbon 4. Let's take a look at carbon 4. Does carbon 4 have 4 unique substituents? Does carbon 4 have 4 unique substituents? Is carbon 4, does it have any 3D shape? No. So this is planar. It's just flat. It's not a chiral center. So remember, chiral centers are overwhelmingly sp3 hybridized because we need to have 4 different substituents and we need to have the possibility of different 3D shapes for different arrangements of those substituents. Does that make sense to everyone? So planar carbons are not typically chiral centers. Carbon number 5, we have a hydrogen, this ester functionality, and a carboxylic acid functionality, and an amine. So this would be a chiral center. So carbons 3 and 5 are chiral centers. I'm pretty shocked actually for all the biologists in the room who were staring at this molecule. I'm surprised I didn't see a snap answer that carbon 5 is chiral. Would someone like to tell me, or would someone like to volunteer and take a guess? Does this motif look familiar to everyone? Does this motif right here look familiar to everyone? Where is that motif commonly found? What type of fundamental molecule is this motif found? Don't be shy. It's the building block of life. Exactly, yep. Amino acids. This is a fundamental amino acid building block. Amino acids have chiral centers, and that's really important for both biological system, biological recognition, and sort of the origin of life as we know it today. Okay, so the key takeaways from this discussion: a chiral center has 4 different substituents. Planar carbons are almost never chiral centers, and chiral centers are overwhelmingly sp3. Does that make sense to everyone? For those who answered 4 and 6, did that clarify? Does that make a lot more sense? Okay, perfect. So let's talk a little bit about chirality centers and chiral molecules. So groups are considered quote unquote different if there is any structural variation, okay? In cyclic molecules, one way that we compare is by following in each direction of the ring. So in method number 1, we're going to count carbons clockwise. In method number 2, we're going to count carbons counterclockwise. And if we have the same groups with the same numbers of counting, then we can conclude that the substituents are identical. Okay, so let's show an example of this. So methyl cyclohexane. Let me show you a model of this, as this will really drive the point home as to why this molecule is symmetrical. Okay, so here is methyl cyclohexane in all of its glory. And one thing I'd like you to note is if we cut methyl cyclohexane right down the middle, are our substituents on each side the same? Do we still have the same number of carbons in each half of this molecule if we cut it directly in half? Is methyl cyclohexane, does it have an axis of symmetry? I see a lot of people typing yes. That's exactly right. And one way that we can check in a really sort of procedural way is we can number our carbons. And the one thing I'd like you to focus on, let's look just at our right hand and left hand groups. So on our left, we have a methylene. On our right, we have a methylene. So this methylene has numbers 2 and 6. This methylene has numbers 2 and 6. Does everyone notice how the methylenes have the exact same number? So we have the same substituent with the same number. Where the methyl group, so does the methyl group, so if we're dividing along the axis of the methyl group, what we're essentially doing is we're comparing all of the groups on the left and all of the groups on the right, and we're checking if they're identical. In this case, the groups on the left and the groups on the right are fully identical. And as a result, this molecule has an axis of symmetry. And so that methyl center is not a chiral center. So to help everyone visualize this counting method, let's showcase our counting method on these structures below. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And as we notice, the methylene, so a methylene, the same functionality, has the same number in both of our counting methods. And if we repeat going all the way around the ring, all of our substituents have identical numbers in both counting methods. So as a result, what we're essentially saying is we have a chiral center with a methyl, a hydrogen, and 2 propyl groups. Now, if we have 2 identical groups, is this center going to be chiral? If we have 2 identical groups, will that center be chiral? No, exactly right. This is an achiral center. Again, this is just another way of checking for an axis of symmetry. Let's now look at 2-methyl cyclohexanone, and let's try this counting method on 2-methyl cyclohexanone. So first things first, I'm going to count. I'm going to choose counterclockwise, 1, 2, 3, 4, 5, 6. And now let's choose the clockwise method, 1, 2, 3, 4, 5, 6. So to give you a sense of what this would look like, so just in our model kit, if we suddenly have an oxygen on our ring, now if we try to cut this molecule in half, is it symmetrical now? Is 2-methyl cyclohexanone symmetrical if we try to cut it in half now that we have this oxygen? No, that's exactly right. And we can show that using our counting method by looking at the number for our ketone. So here the ketone has a number 6. In our clockwise counting method, the ketone is given number 2. So then, because we have different numbers, ergo, we have they are different substituents. So different numbers, essentially, if you see different numbers in both of your counting methods, that tells you that this center is chiral, because the substituents on the left and right-hand side of the ring are different. Now I want you to just take a moment and let's look at a few molecules and let's try to list the chiral centers in the following molecules. So let's list the chiral centers in the following molecules. And some of these examples are ones that we're going to revisit once we have a little bit more information. So I'm going to number some carbons here, 1, 2, 3, 4, 5, 6, 7. And just for this structure on the left, I'd like you to take a moment and type in chat, which centers are chiral centers? What centers have 4 different substituents? And I'm going to draw out the hydrogens. Make sure to check for axis of symmetry whenever you can. So let's take a moment. Let's type in chat now. Which of these centers are chiral centers? Which of these centers have 4 different substituents? So would someone like to volunteer? I see some people typing. Let's get a few more answers before we discuss. I see a lot of people typing 2. That's exactly right. We have 4 different substituents. 1, 2. Let me use a different color pen for this to make things easier to see. So in terms of our 4 different substituents, we have a phenyl, a methyl, a hydrogen, and this complicated chain. Perfect, yep. So 2 is definitely chiral. Any other chiral centers? I see a lot of people typing 6. 6 is also correct. We have 4 different substituents. Would someone like to explain, so for those who answered carbon 4, are planar carbons typically chiral? Are planar carbons typically chiral? Not really. So we have 2 and 6, and I see a lot of people typing 3. 3 is exactly right. Yep, it also has 4 different substituents. So this molecule has 3 chiral centers. Does that make sense to everyone? A chiral center is a center where we have 4 different substituents and there's no axis of symmetry. Does that make sense? Can I get some feedback in the chat just to make sure everyone's comfortable with that? Yes, chiral has to be sp3 in 99.9% of cases. Let's take a moment and let's look at the second example. 1, 2, 3, 4. So take a moment, let's look at all of our carbons and let's assign our chiral centers. So what centers are chiral in the molecule on the right? Let's get a few more answers in the chat, just so that way we have a nice discussion, nice class consensus. Yep, I have people typing 2 and 3. That's exactly right. But when you, what I want you to do is when you see molecules like this with a potential axis of symmetry, we're going to put a big star next to this one because this molecule has some exceptions. And we'll talk about this in the context of quote unquote meso compounds. So we're correct in assigning these 2 centers as chiral centers, but there are certain stereoisomers of this molecule that are actually achiral. And we'll show that when we talk about mesoisomers. But the answer for 2 and 3 for this question was spot on, exactly right. Is everyone comfortable so far? Is everyone following so far with this lecture? Okay, so let's do some more examples. Let's do some more examples. Not necessarily. So if a molecule has a chiral center and it lacks an axis of symmetry, then the molecule itself is chiral. There are molecules that have centers that are there are molecules that have, from this definition, what would be a chiral center, but because they're symmetrical, the molecules themselves are achiral. So it's like if a molecule has chiral centers and lacks an axis of symmetry, then it is chiral. And we'll see some examples as to why the definition is a little bit nuanced. But for example, this molecule on the left, it has chiral centers. The molecule itself is chiral. This molecule on the right, it has chiral centers, but there are certain stereoisomers, such as we discussed last time, where we have an axis of symmetry. We call this a meso compound, and this molecule is achiral. Chirality really depends on whether or not your molecule can exhibit non-superimposable 3-dimensional shapes or non-superimposable mirror images as our basic criteria. Does that make sense? Does that help clarify, Christine? Okay, perfect. So let's look at the following pair of molecules and let's label all the chiral centers. So I'm going to label this A and B. And I'd like you to type in the chat your responses for, let's start with A. What centers are chiral in A? What are our chiral centers in A? Yep, exactly right. Everyone's really fast at this. Carbon 2 and 3, spot on. These are our chiral centers. They have 4 different substituents. Let's take a moment and let's look at question part B. So which centers are chiral in structure B? What carbons are chiral? Okay, I see a lot of people. So 3 is the only chiral center. And would someone like to talk a little bit? So if we look at center 2, So we have a methyl, an alcohol, and an R group, okay? Does carbon number two have 4 different substituents? Does carbon number 2 have 4 different things on it? Nope, it has 2 methyl groups, exactly right. So as a result, this center is achiral. It has an axis of symmetry that we can draw like so. You can split it right down the axis in between the 2 methyl groups. So this is not a chiral center. So this molecule overall only has 1 chiral center. The reason why you want to pay attention to chiral centers is because not only do they affect your design when you want to prepare molecules, but it also affects how many possible stereoisomers, how many possible different 3D shapes you can draw for a given molecule. Good, so I'm really pleased with how everyone's been doing so far. What we're now going to do is really focus on a step-by-step guide on how to draw enantiomers. So enantiomers, remember, are a pair of molecules that are non-superimposable mirror images. Remember your hands, how they don't perfectly overlap? They're non-superimposable mirror images. Okay. Enantiomers, more specifically, have the opposite configuration at every chiral center stereocenter. Okay, so they're completely flipped. So here's the goal. Here's the trick. You draw your molecule, you draw a mirror plane, and there are some options. You can draw it behind, under, or next to your molecule. Okay. So here's an example. Here's an example of a mirror plane behind your molecule. And now this is really cool. If you have like a portable mirror handy, or if you have like a mirror in your bathroom, you can literally take your model kit and hold the model kit up to the mirror, or hold the drawing up to the mirror, and you'll notice how the mirror flips your molecule, right? What we're drawing here is the mirror image. So like if this is your molecule and it's looking into the mirror, so this is our mirror. Now, when the mirror plane is behind your molecule, let's show what's going on here. Let's show what's going on here. So in this case, our methyl is pointing out of the page, okay? Right? Does everyone notice how in this bottom structure for our wedge, the methyl is pointing out of the page? Does that make sense to everyone? The methyl is jutting out towards us. Okay. Now in the mirror image, your methyl now gets a dash. It's now moving into the page. So in effect, what has happened? And let's show this from like a side-on view. Let me make a model kit to help show this. Give me one moment. I'm just putting together the model kit to help everyone see what's going on. Okay. Okay. So in your view, so initially, we have our ring, okay? We have this methylene group, and we have our nitrogen atom. So initially, our methyl group is pointing out towards us. When we draw our mirror image, all we're going to do for the mirror image behind is we're going to swap the position of our out and in group. So for our mirror image, is our hydrogen pointing out or into the page? For our mirror image, now that we've swapped, Is our hydrogen pointing out or into the page? The hydrogen, is it going towards you or away from you? This hydrogen right here, is it closer to you? Oh, yep, exactly right. It's pointing out. So in effect, for the mirror plane behind your molecule, you invert the wedge dash notation for each stereocenter, and you draw the molecule in exactly the same way. This is really important. You can't just easily redraw or flip your molecule. And to showcase that, if I flip this molecule upside down, if I flip this molecule upside down, I have not flipped any stereocenter. When I flip this molecule upside down, do you notice how from this view, our methyl group is closer? Does everyone notice how if I just flip my molecule around, the methyl group is now pointing towards us? Does everyone see that? So here's what I did. I didn't flip any stereocenter. I literally just turned my molecule around and changed our view. This is why when you draw enantiomers, when you follow these rules, you need to draw the molecule exactly the same, okay? You can't redraw it however you want, because when you rotate your molecule, all of your stereocenters and how you're viewing your stereocenters will rotate slightly. Does everyone understand this critical point? So does everyone notice how I drew my main chain exactly the same? Okay, so let's do some practice now. Let's take the following molecules. Let's take the following molecules. These two molecules are enantiomers. Oh, so we're going to take our molecule and we're going to draw up here our enantiomer. So let's focus on drawing our enantiomer, and I'll start off with an example. So if I'm drawing with my mirror plane behind my molecule, I'm going to draw my main chain exactly the same. However, I'm going to flip every stereocenter. So our amine is pointing in. Now my amine is pointing out. My alcohol is pointing out. Now my alcohol is pointing in. So to help everyone visualize these two enantiomers, I'm going to make a quick model kit for you all, and then I'll allow you to compare and contrast the two models. So let's do that really quickly. I'm just going to put together a small model for you. And while we're doing that, I'd like you to try to draw the enantiomer of the structure on the right. And then once we have that drawn, we'll come together as a group to discuss, and we'll compare, and we'll check to see if we did everything correctly. Let's work on drawing the enantiomer of the structure on the right. And you're welcome to hit the share screen feature and share the structures that you've drawn, or to draw using the annotate feature on Canvas or via Zoom. I'm almost done putting together both of the models that we'll need for this session. Any questions so far? Any questions drawing? Perfect, perfect. For the structure in pink, that looks exactly correct. That's exactly correct. You drew the molecule exactly the same, and you flipped all the stereocenters. So to show everyone a model of what this would look like, let me get my two molecules together. Okay, so first things first, on the left, we have the original molecule with our OH pointing out and our amine pointing into the page. And now we have our enantiomer. And in this case, in our enantiomer, is our amine pointing out of the page or into the page? Is our amine pointing out of the page or into the page in our enantiomer? Out, exactly right. So we draw the following. Exactly right. Perfect. Wonderful. So let's talk about the next method. So if we have a mirror plane below our molecule, you're going to invert your molecule vertically, and you're going to retain the same dash wedge notation. Now this is really important. So you're inverting your molecule vertically, and you keep the dash wedge notation exactly the same. So we're just flipping our entire molecule 180 degrees. Notice the wedge stays the same. We have flipped this stereocenter, but the wedge stays the same. Okay, to show you and to help you see the fact that these two molecules here are enantiomers, let's take a moment and let's appreciate and let's observe how to rotate molecules and how to visualize the rotation of molecules. This is a really critical foundational skill that you'll need to develop. So I'm going to start by showing you a model. Of this first structure here. So we're starting off looking at structure 1. Okay? And one thing I'd like you to appreciate is the methyl group pointing out or into the page. Is the methyl group pointing out or into the page? Out. Okay. Now, to draw the enantiomer, I am going to flip my stereocenter, and then I'm going to invert my molecule 180 degrees. Let me show you the molecule now after we have inverted. Okay, so our methyl group is still pointing out of the page, but does everyone notice how our ring and the connectivity in our ring has changed, as well as the position of our amine group? Does everyone notice that change? Now, to help everyone visualize what's going on, I'm going to take this enantiomer, I'm going to rotate it 180 degrees, and then so I've rotated 180 degrees now, and what do we notice about our methyl group? Is our methyl group still pointing out of the page? Is our methyl group still pointing out of the page? No. Now, how is it pointing? Now, how is it pointing? Is it pointing out or in? Into the page. Exactly right. So to showcase this rotation that we've done, what we've done quite simply is we've rotated our carbon-carbon bond, and then we have rotated our carbon-carbon bond on our adjacent carbon, so that way both of our skeletons are arranged in the exact same pattern, okay? Then we compare our methyl groups and we notice one methyl group is pointing out, the other methyl group is pointing into the page. You want to be comfortable playing with a model kit just to verify that when you perform these mirror plane inversions to draw an enantiomer, that you've actually drawn your desired enantiomer. And the way to check that is just compare your original structure and your new structure, and you see immediately that the stereochemistry is different at our chiral centers. Does that make sense to everyone? Does that logic make sense? Does everyone understand how we rotated these molecules? So the wedge notation changes during rotation. Okay, so let's start off from the start. Let's start off from the front. Okay. So here is our original view. So here is our original view. The skeleton is such that we're attached to the top carbon of our ring. Our amine is pointing up in the zigzag pattern, and our methyl group is out of the page. We draw our enantiomer. So our enantiomer, in effect, flips our stereocenters. So our enantiomer looks something like this, whereas we notice our methyl group is pointing away from us into the page. To showcase that it matches this structure here, what we have to do is we have to flip our entire molecule 180 degrees. And then once we set it up that way, once we flip our molecule 180 degrees, as we notice, our depiction of this structure matches right down here. And as we notice, when our molecule is flipped 180 degrees, in our enantiomer, it looks like our methyl group is pointing out. Can you see that visually now? So this is why perspective is really important, because if you start turning your molecules, you need to pay special attention to make sure that you are still drawing the enantiomer. And that's really just to show, even though both of these structures have a wedge, they have different three-dimensional shapes and are different stereoisomers. They're enantiomers of each other because we're just drawing these molecules from a different perspective. That's why they both have a wedge. If we draw them in the same perspective, we see one has a wedge and the other has a dash. So this is really the importance of how you look at your molecules and how you rotate your molecules is really critical when drawing your molecules to ensure consistency. Does that make sense? This is why you have to be really careful with how you draw the skeleton. So with that said, I'd like you to take a moment and use the annotate tool via Canvas, and I'd like someone to draw the vertical mirror image of the following molecule. So this is the mirror plane below your molecule. It's as if the molecule is looking at the mirror from above. And I'd like someone to break out the annotate feature and try drawing this molecule. Yep, good, good. All the stereocenters are being kept consistent. That's perfect. Yep, looks good. Yep, looks perfect. Looks perfect. That's exactly right. Awesome. So both of these responses are spot on. So what I'm going to do really quickly is just clear the annotation. And then let's talk through and let's write out our instructor solution. Yep, so it's exactly right. You flip your entire skeleton, but you keep your stereocenters exactly the same. Perfect. Exactly right. Wonderful. And I'd like you, if you want to at home, you can prove to yourself with a model kit that these two structures are actually non-superimposable mirror images. Let's look at one other mirror plane. This is a mirror plane next to your molecule. So we invert our molecule horizontally, but we retain the same dash wedge notation. Okay? So we are changing how our skeleton is drawn. And to help you visualize what's going on here, let's return to our same example. So if we're just reflecting a molecule across the horizontal axis, how is this methyl group facing right now? Is it facing out of the page or into the page? How is this methyl group facing? Out. So if we flip this entire molecule 180 degrees horizontally, so if we flip this entire molecule 180 degrees horizontally, so let's show where we started from once again. So here's our starting point. Now we're going to flip our molecule 180 degrees. And as we notice, what has happened to our methyl group if we're just rotating our molecule? If we just rotated our molecule, where does our methyl group end up? In. Okay. Now let's look what happens. If we draw our enantiomer. So I'm going to flip my stereocenter. And now we're going to invert this molecule 180 degrees. Now my question to all of you is, for our enantiomer as drawn, what happens to our methyl group for our enantiomer when we flip? For our enantiomer, if we draw our enantiomer using the horizontal mirror plane, where is our methyl group? Is it going out or in? Out, exactly right. So these two molecules are enantiomers. So you don't have to pay attention to just dash or wedge, but also the relative position of substituents. You also have to pay attention to the skeleton of your molecule. So to showcase in fact that these two molecules are in fact enantiomers, let's take a moment, and if we compare via rotation, so let's showcase this. And I really find seeing is believing. So let's start off. So here, one moment. So here is our first structure. So here's our first structure. Okay. Now, what we're going to look at is how the enantiomer stacks up. So if we draw our mirror image, let's go through the steps and let's talk a little bit about how can we compare our enantiomer to our original compound. So our enantiomer looks very similar to our original compound, except it's been flipped 180 degrees horizontally. So the fastest way to undo that flip is to just take our molecule and flip it back 180 degrees. Then from here, all we have to do is rotate our bonds so that our amine substituent is in the same pattern as in our original structure. And now, as we notice, our hydrogen is now pointing out instead of our methyl group. That's what we see right here. So these two structures are enantiomers. You always want to check that. So let's take a moment and let's try to draw the mirror plane enantiomer of the following molecule. Yes, you still want the amine facing up. You want the skeleton to be exactly the same, so that way you can compare the relative positions of your other substituents in the stereo center. Yep. In general, you want your skeleton, if you're comparing two structures, you want the skeleton to be drawn in the same way, so you can check to see whether your wedge dash notation has changed. That's exactly right. So let's take a moment now and let's use the annotate tool to try to draw the enantiomer for the following molecule. And don't be shy to break out the annotate tool. It's right in the Zoom overlay. And I always like to see people providing their drawing input, since it's hard to communicate some of these structures verbally. So don't be shy and try to draw the horizontal mirror plane enantiomer for the following molecule. So you're essentially drawing the horizontal mirror image, just like your hands are horizontal mirror images. And don't be shy. Sure, for another example, I guess we can do this extra one. Yep, we can do that. So in terms of our enantiomer, let's take this molecule and let's reflect it and invert it across the horizontal plane. So we're essentially inverting our molecule 180 degrees. So I'm going to draw the same skeleton, except reflected 180 degrees. And then at this carbon here, if I reflect it about the mirror plane, I get the hydrogen in the same spot, the chlorine in the same spot, except my whole molecule has been flipped 180 degrees. So you essentially draw the horizontal mirror image of your molecule. While keeping in mind the chlorine is down in one enantiomer, it's down in this second enantiomer. However, this center has a different configuration. And this molecule has a different 3D shape. Does that make a little more sense, Vaden? You're essentially drawing the horizontal mirror image, keeping all of the stereocenters the same. So the reason why this configuration is different is, although in both cases the chlorine is down, we have changed the relative positions of the substituents attached to the chlorine. So for example, if I were to assign numbers to this, if this was 2 and 3, the relative position of our other groups in our molecule has changed, right? Do you notice how 2 and 3 are in different spots relative to each other? So we'll talk next actually about formal methods of assigning configuration, but essentially this configuration is an R in that the relative position of our numbered groups is clockwise to each other, while this stereo center would be S, as the relative position of our groups is counterclockwise. This is where, and one of the real strengths of our method for assigning R and S configurations in a standardized manner is it makes it very easy to see that the three-dimensional arrangement of our stereocenters is different. So it's hard to see with the models sometimes, or it's hard to see just staring at the pen and paper without making a model. But once you start formally assigning each center as R or S, it becomes really clear to see that the relative position of your substituents has changed. And as a result, this molecule has a different 3D shape. Does that make sense? So it's not just the relative position of hydrogen and chlorine, but the position of every other group in your molecule that has changed. On that note, what we're next going to delve into is a brief little review of optical activity. So let's talk a little bit about optical activity, as it's a critical idea into understanding where we began to start to get a sense that molecules were chiral, and a way to measure the purity of chiral compounds. So light restricted to pass through a plane is known as plane polarized light. A polarimeter measures the rotation of plane polarized light that is passed through a solution. So as the light source passes through a polarizer, it's then detected at a second polarizer. So the angle between the entrance and exit planes is known as the optical rotation. So plane polarized light that passes through achiral compounds retains its original plane of polarization. Now, and this is the key part I want you to take away from this. Solutions of chiral compounds rotate plane polarized light, and the molecules are said to be optically active. Okay? So chiral molecules rotate plane polarized light. Okay, so we can measure and we can quantify this by measuring the rotation in degrees. So if it rotates plane polarized light in a clockwise manner, we call it dextrorotatory. It's depicted with a positive sign. So your alpha will be positive, your optical rotation will be positive. Anti-clockwise or counterclockwise is known as levorotatory, and it's depicted with a negative sign. Now, one thing I want you just to immediately establish, dextrorotatory and levorotatory have to do with the measurement of optical rotation. They have nothing actually to do with the exact configuration of your center. And that's a little unfortunate, but that's how nature works sometimes. The specific rotation is a standard measure of optical rotation. It's the observed rotation over the concentration divided by the path length. Now, a key feature of enantiomers is that the specific rotation of enantiomers is equal in magnitude but opposite in sign. So for example, if we compare SS and RR tartaric acid, or minus tartaric acid and plus tartaric acid, minus tartaric acid has an optical rotation of negative 12 degrees, while plus tartaric acid has an optical rotation of plus 12 degrees. So if you ever see optical rotation values, I just want you to know the specific rotation of enantiomers are equal in magnitude, opposite in sign. Okay. Now for some word of caution. And this is something that I really want to drive home, as it's a trick question that's sometimes asked on the ACS. There's no simple relationship between RS and the direction of optical rotation. So, for example, the sign of optical rotation can sometimes change based on solvent, concentration, and other factors. So don't relate the plus and S in any way, or the minus and R in any way. The plus and minus, so when we think plus and minus, that has to do with optical rotation. The R and S has to do with the stereochemistry. Enantiomers have opposite stereochemistry and opposite optical rotation, but there's no clear correlation between R and plus or minus, okay? So just to give you a sense of some things, here are some molecules. So for example, penicillin, cholesterol, sucrose, and you notice the optical rotations really vary depending on the compound. For chloroform and acetic acid, let's focus a little bit on that. So chloroform is CHCl3. So this is chloroform, and acetic acid is CH3CO2H. Would someone like to comment, and would someone like to explain to me, why do we see an optical rotation value of 0 for chloroform and acetic acid? Why do we see an optical rotation value of 0? What is our key criteria? When do we see an optical rotation value of 0? So let's think about that for a moment, and if someone would like to answer. Yep, exactly right. These two molecules are achiral. Wonderful, exactly right. They lack a chiral center. They don't have a carbon with 4 different substituents. Wonderful, exactly right, perfect. So, enantiomeric excess. Let's talk about enantiomeric excess, or EE. It's a commonly reported value in the literature to describe the efficiency and selectivity of chemical reactions. So, one enantiomer of a compound can have a greater biological activity, or it can even have the desired biological activity. Now, when we think about why that is, we'll talk, R and S has to do with stereochemistry. We'll talk more about that in the next section on methods for assigning stereocenters as R or S. So don't worry, we'll get to that. Now, in terms of part of the reason why we think biological systems respond differently to different enantiomers is that biological systems and receptors are chiral, and they can differentiate compounds based on their configuration and shape. Now, the amino acids that comprise our peptides and proteins are chiral. They have an S configuration except for cysteine. So it's sort of like a handshake. You can know whether you're shaking someone with your right or left hand and whether they're shaking your hand with the right or left hand. And as a result of these interactions between chiral molecules, different molecules have different binding affinities and bind to different receptors based on their configuration and shape. This is the quote-unquote lock and key model. So if it's able to perfectly match the receptor and has the right shape to perfectly match and bind to the receptor, a molecule will have that activity. I mean, just intuitively, you can clearly tell if you're using your left hand to shake a person's right hand. Just like we can sense that interaction between chiral species, molecules can sense interactions depending on the chirality of the molecule binding. Okay, so let's talk about some practical examples. So if we think about ibuprofen, classic pharmaceutical agent, only the S enantiomer of ibuprofen is biologically active. The R enantiomer is just useless junk that's generated and is along for the ride. Now, enantiomers, we can also see more dramatic effects where for penicillamine, the S enantiomer can be used to treat chronic arthritis. It was actually a pretty common arthritis treatment if it weren't for this unfortunate little rider. The R enantiomer is highly toxic. So just a mild difference in the stereochemistry results in a substantial difference in activity. One is toxic, one has a beneficial pharmaceutical effect. So we do need to be able to accurately assign and determine whether something is the R or S enantiomer, and we need to be able to determine the purity of our mixtures of enantiomers. So key features we want to take away from this: we have a desire and there's a need to separate enantiomers, or we need to prepare enantiomers as single pure products. Further, we need methods to determine the purity and amount of each enantiomer in a mixture. And for that, we can use optical rotation. Okay. So, measures of enantiomeric purity. There are two main methods. Enantiomeric excess, which I personally like a lot. This is the standard. It's the percent of the desired enantiomer minus the percent of the opposite enantiomer. So as an example, if a reaction makes a mixture that is 70% of the desired enantiomer and 30% of the undesired, your percent EE would be 70% minus 30%, which is 40%. It's the amount of excess enantiomer produced or isolated. So the other measure of EE is known as percent EE, which is a measure of the percentage of the desired enantiomer. So percent EE is measured using optical rotation. So percent EE is the observed optical rotation over the optical rotation of the pure enantiomer times 100%. I personally don't like percent EE as much as straight enantiomeric excess because percent EE describes a ratio. Well, I really want to know how much extra of the desired enantiomer am I making? How much selectivity am I getting for the desired enantiomer? So I don't like percent EE as much personally. Okay, so those are our measures. Now we're going to talk, and this is going to be a pretty bulky section. We're going to talk next about how do we assign configurations for chiral centers? What is our standard method for assigning configuration at chiral centers? So the go-to method is known as the Kohn-Ingold-Pringold prelog system. And these are known as sequence rules developed in part by IUPAC. So this is the standard for naming stereocenters. So let's talk about each of the rules step by step. So first and foremost, we're going to look at the 4 atoms directly attached to the chiral center and rank them according to atomic number. So atomic number is the key in this case, okay? That's what we care about. The atom with the highest atomic number is assigned a 1, the highest priority. The atom with the lowest atomic number is assigned the lowest priority of 4. So just as an example, we'd assign our priority. So looking at our atoms, so we have carbon, chlorine, bromine, and hydrogen. What is the highest atomic number atom attached to this central carbon? What's the highest atomic number atom? Bromine, yep. So bromine would get a 1, chlorine would get a 2, carbon would get a 3, hydrogen would get a 4. Perfect. Let's do another example. So if we compare sulfur, oxygen, fluorine, and hydrogen, what atom gets the highest priority number? What atom gets the 1? Yep, sulfur. Okay, what's after sulfur? Yep, fluorine, exactly right. And what's after fluorine? Oxygen, yep. Perfect, perfect. Wonderful. So far, so good. Now, if 2 atoms have the same atomic number, you then have to make a list of each atom connected to each atom connected to the chiral center. You rank the atoms connected in order of priority. If a list has a higher priority group, this is not the total, just a higher priority group, you assign that atom the higher priority. Now, if for some unfortunate reason, if your lists are identical, you keep moving one atom away and you rank the atoms attached in order of increasing priority. Just as a side note, multiple bonds, so double and triple bonds, so multiple bonded atoms are equivalent to the same number of single bonded atoms. So for example, a carbon-oxygen double bond can be thought of as a carbon bonded to 2 oxygens. This will be really important as this often can be a tiebreaker when assigning priority. So let's talk about the second rule. So let's suppose if you have 2 atoms with the same atomic number. So we're going to have to make a list of each atom connected to each atom connected to the chiral center. We rank the atoms connected in order of priority. And if a list has a higher priority group, that atom gets a higher priority. Okay, so let's do an example. So looking at the following molecule, so we have a carbon, an oxygen, and a hydrogen. So what is our highest? The highest priority group has the highest atomic number. So for example, in this molecule, what would be the highest priority group attached to our chiral center? So we look at our chiral center, and what is the highest atomic mass group attached? Oxygen, yep, exactly right. So the oxygen gets a 1, yep. Now, in our tiebreaker, we have a carbon. So we have 2 carbons. So these carbons are tied, right? They have the same atomic mass, right? Carbon and carbon, same atomic mass, okay? So now what we're going to do is we're going to put a dot, and now we're going to make a list of everything attached to these carbons. So attached to carbon number 1, we're going to make a list. So first things first, we have a carbon, okay? So we have a carbon right here, right? We have another carbon and 2 hydrogens. Okay, let's look at carbon number 2 now. Carbon number 2, we have a carbon, another carbon, and 2 hydrogens. Do we still have a tie? Do any of these carbons have a higher priority group? Do we still have a tie? Looking at our lists. Is there any higher priority group on the list? Yep, there's a tie. Okay. So now we're going to keep moving over. Now we're going to move to the next carbon. Okay, and then we're going to compare. Attached to this secondary carbon, we have a carbon, a carbon, a carbon, and a hydrogen. Wonderful. Okay. Attached to carbon 2, we have a carbon, a hydrogen, and a hydrogen. So as we notice right here, does carbon have a higher atomic mass than hydrogen? Does carbon have a higher atomic mass than hydrogen? Yes. So which carbon wins out? The carbon on the left or the carbon on the right? Which one wins out in terms of priority? Left. Exactly right. Exactly correct. Just to avoid that unfortunate double meaning. Okay, so then we're going to assign the carbon on the left as number 2, the carbon on the right as carbon 3, and the hydrogen gets a 4. Does that make sense to everyone? Does that logic make sense? Let's do another example. So looking at the following chiral center, what is our highest atomic mass? What's our highest priority group attached to our chiral center directly? Yep, so our oxygen gets a number 1. Now let's compare our 2 carbons. Is there any difference between these carbons whatsoever? Initially, just looking at carbon versus carbon, are these the same atom? Well, they're both carbon, and the reason why people are typing no is because if we look one step over, so if we make a list for this carbon, so let's make a list for each of these carbons. So attached to this carbon, we have an oxygen, a carbon, and 2 hydrogens. To the carbon on the right, we have a carbon, a carbon, a carbon, and a carbon. So which one wins out? The carbon on the left or the carbon on the right? Which one wins out? Which one has the highest atomic mass group? Left, exactly right. Oxygen wins out. So it doesn't matter your total priority. It doesn't matter your total atomic mass. It only matters if one atom has a higher atomic mass than the other atom on the list, right? It doesn't matter that we have all these extra carbons. It's the fact that oxygen has the highest atomic mass in both of these lists, so the carbon on the left wins out. So the carbon on the left gets a number 2, carbon on the right gets a number 3, hydrogen gets a 4. Does that make sense to everyone? Okay, so what we're going to do is we're going to take a quick break. We're going to resume in 10 minutes and we'll continue this lecture and wrap up a few more topics in laboratory for about an hour and a half. So at this time, I'll be ending the recording.